start recording here. Okay, so we move from section 3 to section 8.4, where we look at some other convergence tests. And of course, I'm going to give you a chance to copy the examples down. But like, what if you look at like the first series here, what makes that series a little different compared to the series that you've seen before? Think about that. Let me let you copy the example down, all right? And then we'll talk about that. Okay, so, all right. As always, we want to determine if series converge or diverge. And looking at series A, looking at the section 8.4 here, looking at the terms of this series, what are the terms? I mean, that series, does that look, do the terms remind you of a series that you've seen before? 1 minus a half. Let me just go. 1, a half, third, fourth, you know, and so forth. Do those terms remind you of a series that you've seen before? That's right, Tina. That's right, Colomb. It's a harmonic series, but there's a difference here. Our harmonic series would be like if you had 1 plus a half plus a third plus a fourth, okay, and so on. That would be where all a harmonic series, all the terms are positive. And this the harmonic series here, that series does what? Does it converge or diverge? A harmonic series. You remember? So harmonic series that diverges. That's right, Rodrigo. That's a harmonic series, and it diverges. So even though, yes, the terms are approaching zero, they're getting smaller and smaller. Nevertheless, they're not getting small enough at a fast enough rate for the series to converge. So this series diverges. And I'm writing it kind of quickly because you've seen it before. What we have, though, here in our series in A is what's called an alternating harmonic series. The terms go plus one minus a half, plus a third minus a fourth, plus a fifth minus a sixth. It's what we call an alternating harmonic series. And the question is the fact that some of the terms are negative, half the terms really are negative, does that help the series to converge? And the answer is yes. So let's go to the solution for A here. We'll do this one at a time. So there is a theorem called the alternating series test. And what it says is two things. So the terms of this series, we're not going to worry about the plus or minus right now. I mean, it is important for convergence, but we're going to call B sub n, we're going to let it be 1 over n. Because that's, the terms of the series, 1, a half, a third, a fourth, and so forth, that's found by 1 over the sequence 1 over n. But of course, the terms are positive and negative, but we don't worry about that right now. So first thing is, do the terms of the series decrease? And they do. The terms of our series decrease because, and this is just a fancy way of saying that, if you look at the n plus first term, that equals 1 over n plus 1. That's less than the nth term of the series, which would be the previous term of the series, 1 over n. So the terms of the series decrease. If you disregard the plus or minus, the terms of the series decrease. But also, that's the first condition. The second condition is that do the terms of the series approach zero? And they do. So that is enough then, if you have an alternating series, to say that the series converges. It's only because you have this alternating series where the terms go plus, minus, plus, minus, plus, minus, plus, minus, and so forth. That's why you have, that's why that series will converge. Okay, and I'd like to show you this in the book to give you a visual feel for this. Okay, Kahindi, you can't, very good question. You can't use the alternating series test for a harmonic series because a harmonic series, the terms don't alternate back from like positive, negative, positive, negative, positive, negative. A harmonic series is not a alternating series. But an alternating series is one where the terms go positive, negative, positive, negative, positive, negative forever. Okay, and if we look in the book here, I'll come back. I mean, let me just show you in the book here real quick. Let me go in the ebook. Okay, so section 8.4 is going to deal, I mean, the tests that you've seen so far apply only to series with positive terms. In section 8.4, you learn how to deal with series whose terms are not necessarily positive, like this series we're looking at, the alternating series. So what the situation is, I mean, the alternating series test, I actually just showed that it applies, for our series. And again, if the terms of the series are decreasing, that's the first part of the test. And then if the terms of the series approach zero, then our alternating series is converging. And the way you can sort of think that is by this little figure here, figure 1. Basically, they look at the partial sums. You see here on the figure 1, the axis goes like S sub 1. Okay, S sub 1 is the sum, is just the first term. S sub 2 would be B1 minus B2. So S sub 2 goes over here to the left. But then if you add B sub 3 to the second partial sum S sub 2, then you get S sub 3. But because you're adding a positive term, that moves the partial sum to the right. So S sub 3 gets moved to the right. And then the fourth partial sum is by adding -4 to S sub 3. That moves the fourth partial sum, it will be to the left. So what happens is, if you continue this, the partial sums keep oscillating back and forth about eventually what the true sum is, the true sum S. Okay, so like it says, continuing in the manner, the partial sums oscillate back and forth, and they oscillate back and forth about that true sum S. So it seems plausible that the partial sums are converging to the sum S, which is the sum of the series. And so that's the idea behind the alternating series test, is that, if you look at the partial sums, if you keep taking partial sums, they're going to oscillate back and forth. Okay, because the terms, the sums you're adding, you are adding a positive term, and then you're adding a negative term, but the terms are getting smaller. So it causes the partial sums to oscillate back and forth about the true sum, but they're getting closer and closer and closer. Okay, the oscillating back and forth of the partial sums is due to the terms that you're adding switch from positive to negative, and that oscillates the partial sums about the true sum S. But because the terms are getting smaller and smaller, the partial sums converge to the true sum, and that's why that works. Okay, are there any questions on that? Okay, all right. Well, then let me go to, all right. Let's go to B here, and maybe we'll have to stop at B, but let's at least try to get B in. So B series, oh, why that isn't series B is a sum where n goes from 1 to infinity of -1 to the nth power times 3 to the n over 4n minus 1. So what kind of series is B? What kind of series is that? Because of that -1 to the nth power in there. What kind of series may we call that? An alternating series. That's right, Columbus. An alternating series. Now, looking at the denominator here, when n is large, is that -1 going to matter? Is that going to affect it? It is not. That's right, Rodrigo. It absolutely will not. I mean, you know, the effect will be minuscule, minuscule. And so really what we have to focus on is the fact that the terms of this second series here are alternating, but 3n over 4n, if that's the part of the series, you know, that's going to matter when n is large, 3n over 4n equals 3/4, right? So what's going to happen here, I'll just go right to the solution here for B, is that the terms of the series are going to, when n is large, the terms of the series are basically going to act like this: 3/4 minus 3/4 plus 3/4 minus 3/4, and so on. So the terms of the series, the series never settles down to any, never converges to any finite number. Okay, but so intuitively that's why the series doesn't converge. But we can also comment that the limit as n approaches infinity of -1 to the nth power times 3n divided by 4n minus 1 just doesn't exist. Again, because of, we can intuitively see it down here. The terms of the series as n gets large are basically going to be acting like 3/4 minus 3/4 plus 3/4 minus 3/4. You know, the series never converges. So this series diverges by the test for divergence. Okay. Are there any questions on that? Test for divergence was a test that you saw back in section 8.2, but we can use it here for this series. How many find the little comments helpful that I make, like this little comment at the bottom? Is that helping you intuitively to have a feel? Okay, wonderful. All right, Tina likes it very much. Nabil likes it. Excellent, excellent. Very glad to hear that. Very glad to hear that. Okay, are there any questions at all for that particular series? All right. All right, and I'll point one more quick thing out here. Has everybody had a chance to copy the answer here? Good, or well, I should say. Okay, all right. All right. All right, very good, very good. All right, so what we'll do is this example, we've done A and B. We've looked at those series. Series A converged by the alternating series test. Series B, the series in B, diverged by the test for divergence. And what we're going to do on Thursday's class, we'll finish this example and talk about the series in C. All right, so I think I'll stop the recording there.